All right, welcome. Today we're going to start the topic of secure hardware, intellectual property, and in particular we'll look at digital watermarking techniques. So the evolution of hardware, as you all know, has been characterized by an increase in logic density, more transistors on a chip, um, and so at some point uh, you get so many transistors on a chip that one designer and one design can't possibly utilize them all. This is really kind of a turning point in the way that very large scale integration design is done, in that it motivated the idea of design reuse. So the new design method would that would incorporate this reuse would rely a lot on previously designed blocks. So again, we've seen a large increase in number of transistors on a chip. So this motivated the technique of design reuse. Examples where you'll see this: bus controllers, uh, CPUs, memory subsystems. These blocks can be integrated into a design so that these more routine functions don't have to be reinvented every time you begin a design from scratch. This has a lot of advantages. First of all, it saves a ton of time, right? Also, once you test a particular block, you have some confidence in its performance. So you get some performance guarantees, and then the designer can focus on what is actually new in the design that they're creating, right? The actual innovative part of the new design. So this brings up the idea of design intellectual property, right? So what is intellectual property in a design? Well, intellectual property is a unit of the design that can be viewed reasonably as a standalone component. And so it's integrated into the design, but it's functionally standalone in that it is complete in the sense that as a system on a chip, it's a complete design. And these can be physical design blocks, they can be memory, they can be interfaces, routed net lists, algorithms, things that are instantiated in the hardware. And we can categorize them in three ways, into three groups, mainly based on the way they perform and how flexible they are. So there's a group. The first group is called hard IPs, hard intellectual properties. Okay, hard IP. These would include graphical design system files with text lists and a high-level model, the actual customized physical layout, placed and routed right with the net list, um, and instantiated in a technology library. They're, they perform very predictably. Generally, they're optimized for performance, and they're not flexible, right? They do what they're intended to do. They do it well, but they're not flexible or customizable. The second type we have, as you might imagine, is called soft IPs. And soft IP is delivered differently. When you get soft IP, it's synthesizable hardware description language. So you're getting actual HDL, like you're getting Verilog, or you're getting a VHDL program. That's the way that a soft IP would be delivered. And since you're getting the HDL description, you get more design flexibility. But what you're giving up is predictable performance, right? Because you can modify the HDL, and so it's not, since it's not already synthesized and routed and and delivered as an unalterable unit. For this flexibility, you're getting some unpredictability, or some potential unpredictability. And then finally, there are firm IPs, the third kind. So we have hard IP, soft IP, and firm IP. Firm IPs examples would be register transfer level subblocks, fully placed net lists, maybe for some generic technology library. So it's in between the hard IP and the soft IP. Okay, so why, right? Why do we want to secure design IP? Well, given that we're going to have a reuse-based design, the intellectual properties are designed not only for some initial use, but then also, with reuse in mind. So hardware IP vendors work to make sure that their intellectual property is flexible so that it can be used in other designs. And the reason they do this is because they have a profit motive. So there are design standards and design guidelines out in the industry that are agreed upon, that are intended to facilitate reuse, and design engineers need to cooperate and share data, share expertise. So the design details, which include the HDL source codes, are documented by these standards and made public in order to facilitate the reuse of the design. So a lot of the information about the design is out there, for convenience, so that other people will actually use the design, because if you create a design intended for reuse but no one uses it, you're not making any money on it. And there's been litigation going back to the 90s that that relate to semiconductor IP infringement, and this the amount of litigation has increased a lot, and so the revenue loss in the area of IP infringement is estimated to be in the billions of dollars at this point. One way that IP is stolen, and a particularly dangerous way, is by reverse engineering. So reverse engineering is where the device, the object, is taken apart and analyzed. The purpose of this is to duplicate, or sometimes to improve, the original design. Reverse engineering, it's common practice in the hardware industry, sometimes with good intentions, for identifying bugs. If it's your own IP, and you're reversing it to identify bugs or to enhance performance, but also can be a way, the techniques of reverse engineering can be a way to study your competitors' products, stay in pace with technology, right? And this happens not just in the types of logical hardware designs that we're talking about, but I mean, you see it in the automobile industry as well, where designs across automobile manufacturers often look very similar. For integrated circuit products, it's possible to grind away the chip layer by layer very carefully, and then to use technology like electron microscopy to study the layout of each layer, and then some of the details of the integrated circuit can be discerned. Fabricating identical duplicate of the product can be accomplished when each layer is revealed. And it turns out that many times the cost and the requisite skill for doing the reverse engineering is a lot less than it would be to develop the actual product on its own. So the business case is there for piracy of intellectual property. So that begs the question, what is available for securing your intellectual property, right? Clearly, manufacturers are going to want to protect the investment that they made in their IP. In practice, this is mostly done with deterrent and protection mechanisms. So, this can be in the form of a patent or a copyright, trademarking, the use of contracts and trade secrets. And these techniques clearly aren't going to directly prevent the piracy of the intellectual property, but they discourage the misuse because there are consequences if someone infringes on that IP, the recovery of financial loss and things of that nature. The problem is that the owner of the intellectual property is responsible for identifying and reporting IP infringement, and so there's an expense associated with that. It's not always the easiest thing to do. So it's natural to look towards more technical protection mechanisms, such as encryption or dedicated hardware, the use of chemicals to prevent unauthorized access. These are all things that are out there today. We can use standard encryption to protect design intellectual property. The decryption process is expensive, however it is still used. For example, several FPGA design tools give the users the choice to encrypt. Altera's encryption software enables the encryption of the design, and any attempt to compile the encrypted intellectual property will fail if the core is not decrypted properly. Xilinx also adds decryption so I guess starting with the Vertex 2 and Vertex 2 Pro boards, there were options for decryption. The Xilinx design tool can allow the user to select a number of plain text messages and then use them as the key to encrypt the FPGA configuration bitstream file. The decryption unit will decrypt it before configuring the board. Chemicals can also be integrated in the chip for passive protection. And you'll see this more in military devices. So if someone attempts to reverse engineer the chip by um, uh, physically, right, the surface of the die when it is scratched and exposed to the atmosphere, a chemical reaction will occur that will damage the silicon and prevent the attacker from reverse engineering the chip. There's a number of detection mechanisms that are proposed in the research literature, and you're seeing this coming both from academia as well as from industry, and you'll see these applied to virtually every phase of the chip design procedure. Efforts from industry are geared a lot towards identifying and tracing legal IP usage for the purpose of checking and updating, and for royalty reporting, right, directly related to being able to collect royalties for the use of the IP. Academic research tends to be concentrated on protection and deterrence of more highly technical IP piracy methods such as reverse engineering. So to some degree there's a distinction between industry and academic research, and you know, this shows that people are going to look at the same question in different ways, provide different answers, but there may be common context or relevance between the approaches, and in some ways the approaches are often complementary to one another, and so as a result there is some good collaboration in this area between academia and industry. Once piracy is detected, law enforcement needs to be involved, right? So, you know, this is basically a crime, and the way to recover lost revenue due to the piracy, is to involve law enforcement. So the use of encryption and the other protection mechanisms that we've been discussing make piracy more difficult and more expensive, but what is also needed are detection schemes, and this is really where digital watermarking comes in. We need to enable an IP owner to identify the fact that there was IP piracy. This is the first step towards using the legal system to recover royalties when there is an IP infringement. And so that brings up the case for digital watermarking, which is going to be the main topic of the remainder of this talk. Before we get into digital watermarking as it relates to IP, let's back up a second and just talk about what a watermark is in general, right? So watermarking, you may have heard of watermarking as it relates to photography, pictures, and also digital pictures. Digital media has been, I guess, where the original digital watermarking ideas originated, was in digital media. So watermark is essentially, it's a secret message that is embedded into, say, an image or some other data, and the existence of the watermark it's deliberate. You know, the watermark is intentionally put there by the owner of, say, the image, but it doesn't change the way that you see the image. So in say a JPEG, which is a compressed image format, you can change some of the data in the higher frequency portions of the higher frequency data. Essentially a JPEG is, if you start off with an RGB file and you apply a wavelet transformation to the RGB data to get something, you can think of the wavelet transformation or the discrete cosine transformation that is done to get the JPEG similar to a Fourier transform or a Laplace transform, where you're going from time domain signal to a frequency domain signal. Now, if you think about that, you can change the higher frequency data in the final image without changing the how you see the image, the perception of the image. And that's really how it's done. You can think of it also in terms of an audio file, right? If you have an audio file and it has some high frequency content in it, and you change that high frequency content in a very deliberate way that is extractable, but that frequency content is inaudible to humans, then no one's going to notice when they're listening to that audio file that they've that it's been changed. However, you've now embedded a secret message into that file, which can be used to identify that it was actually your property. So mathematically, the watermark allows us to argue that its existence is deliberate. The watermark, the effectiveness of the watermark. So let's make some notes here on digital watermarks. It's just in general, digital watermarks. First, we said that it's a secret message that is embedded in data or some other message, and knowledge of the watermark let's say the secret key allows it to be extracted. And the effectiveness of the watermark is determined by three main things. How stealthy is it? Right? We don't want the watermark to. We don't want anybody to know it's there, or that we don't want them to be able to extract it unless they know the secret. It needs to be resilient in that it should persist even if someone modifies the file. And then the capacity, right? How large can we make the watermark relative to the size of the data that we're trying to protect? Okay, so let's look at the process that's used for watermarking. So we start out with our original image. If we're considering that this is an image file. And then we have the watermark itself. And a key. And then there's an encoding algorithm. These are all inputs to the encoding algorithm. And what we get out is a watermarked image. And as we said before, one of the important things about the watermarking process is that it's robust. So for example, if we just took the least significant bit of every say byte in the image file and flipped it, and that didn't impact the quality of our image file, we still really wouldn't have a very robust watermark, because someone can go in and do the same thing. They can change the least significant bit, and they've destroyed the watermark, and there's no way that we can extract that information back out. So consider another process. Suppose we have spatial domain data in an image file, and if we pseudo-randomly selected pairs of pixels represented by spatial data, and for each pair the expected sum of that pair would be 0, right? The expectation, given that the pairs are randomly distributed. So we can, based on our pseudo-randomly generated secret key, we can increase the first of the pair by 1 and decrease the second of the pair by 1, and now the expected sum of the two would be 2n, where n is the number of pairs of pixels that we selected. And then to detect it, we can do a checksum on the original watermarked image. So that's a little bit more sophisticated method of doing a digital watermark. And the study of digital watermarking and embedding information in digital imagery is, could go on for some time about that. But I really just wanted to introduce the topic relative to imagery, so that you understand the idea of what the watermark is, what it's for, and how it might actually be used. What I want to do now is turn our attention to how would we do this with digital logic designs. How could we take this same idea of digital watermarking and make it apply to digital logic design? So, as we've seen, digital watermarking, digital data watermarking, is hiding a signature in some digital media for the purpose of identification or copywriting or annotation. And the traditional techniques, such as we've briefly discussed here, take advantage of some limitation in perception. We can't see certain changes, or we can't hear certain changes. So it's a limitation in human perception that allows us to really embed minor errors into the file, and those minor errors are the digital signatures. We're changing the original data, and that idea is not directly applicable to hardware design intellectual property, because the value of the intellectual property is incumbent on the fact that it is functionally correct. So randomly changing the data in the IP is not necessarily, or in most cases, is not an applicable method. But the idea still holds. We want to embed some secret into the IP. So how do we do that? One way to do this is to consider that an IP design is really satisfying a constraint problem. So the constraints that we put on the problem are the design requirements. And if we use that idea and extend it, we can say that a constraint-based watermarking technique would translate in signatures that we want to embed into a set of design constraints on top of the original design constraints. And this can be done during the design and implementation of the intellectual property so that we can encode the signature into the IP. So the idea is that creating intellectual property is equivalent to solving a hard problem where the requirements are the functionality for the IP, and those requirements are constraints, and then we place additional constraints. So to hide a signature, the designer would create an additional set of constraints, and these would be created using a secret key. They're selected in a way that they don't conflict with the constraints of the original problem. So we're not violating the constraints, the actual design constraints of the intellectual property. We're just placing additional constraints onto the design that are derived from a secret key. Then the original constraints and the additional constraints are combined, and the result is the solution to a more constrained problem. And this problem is solved instead of the original problem, and then the information, the hidden information, is embedded into the design itself. So the original problem, the requirements for the original problem, or the restraints for the original problem, that is what we were actually designing in the first place, those are called cover constraints. And the requirements that are derived from the secret key that are used to embed the signature are called embedded constraints. And the problem that we solve, which is called a stego solution, will satisfy both sets of constraints. So graphically that would look like this. First we have the original problem, which we're calling the cover constraints. And then there's an embedding algorithm. And the inputs here, well, the inputs are the original cover problem, the cover constraints, and then the signature. And remember, the signature comes in the form of an additional set of constraints that are called the embedded constraints. And then there's a key. And the output of this is the entire set of constraints, or what we're calling the stego problem. This problem is solved. In other words, come up with a design that satisfies all of those constraints. And then, using the solved problem, suppose we wanted to recover the signature so that we can show that we did embed this information. There's an extraction algorithm which uses the original key, and the output is the signature. So now we can show that the information, the signature, or the embedded constraints were intentionally embedded into the design and are extracted with the secret key. Keep in mind that the Stego solution is going to satisfy this additional set of constraints that we're calling the embedded constraints that are the signature, and they're not necessary constraints to the actual design. So you can say that it's unnecessarily satisfying an additional set of constraints, and these constraints will look random if you don't have the signature and the key. However, you can regenerate those embedded constraints with the secret key and the signature and show that they're not actually random. So you can see that there's cryptography involved here. For example, one-way hash functions or stream ciphers can be used to generate the embedded constraints, and there's several approaches that are proposed in the literature to detect the embedded watermark. Let's look at an example of how this might work. So let's consider a relatively simple Boolean function that would represent our design. So consider the function f of a, b, c, and d, and this is going to be in sum of min terms format. So we have a naught, b, c naught, d naught, or a naught, b, c naught, d, or a naught, b, c, d, or a, b, c naught, d. Okay, so if we consider this to be our original set of constraints, or our cover constraints, the goal here is to rewrite the function f in the sum of product format, minimizing the number of literals that we're using. And if we do that, you can verify that the function would look like this. F would be equal to a naught, b, c naught, or a naught, b, d, or b, c naught, d. So we've rewritten the function with 9 literals. This is a unique solution to the min-term problem, and so the size of the possible solutions is 1, right? There's only one solution with 9 literals in it that gives us the same output. So in this case, there would be no room to create additional constraints to put a watermark. But let's assume that we also had 2 don't care conditions as part of the design. And our 2 don't cares are going to be a naught, b naught, c naught, d naught. And a, b, c, d. Okay, so if we treat both of these conditions as 0 output, the function remains exactly the same as it does in our original specification. However, if we want the output to be 1 for our don't care conditions, the function would look like this. So let's just say the original function outputs 0 for both don't care conditions. If we wanted the output to be 1 for the don't cares, then the function would look like this. F of A, B, C, D equals A naught B, C naught D naught, or A naught B, C naught D, or A naught B, C, D, or A, B, C naught D, or A naught B naught, C naught D naught, or A, B, C, D. And this expression can be simplified actually with only 5 literals. So now we have the simplified expression is f of A, B, C, and D is equal to A naught, C naught, D naught, or BD. So the idea here is that we can hide 1 bit of information in each of the don't care conditions. So to hide a 1, we force the output, we force the function to output 1 on that particular don't care condition, and to hide a 0, we remove the don't care condition from the specification and consider the output to be 0 for that given don't care condition. So for example, the original function on the previous page, this one back here, this one carries the information 0, 0 because the don't care conditions are both 0 in this original function. This one that we just created carries the information 1, 1 because both of the don't care conditions are 1 in that case. If we wanted to embed 0, 1, we change our function. So our original terms remain A naught B, C naught D naught, or A naught B, C naught D, or A naught B C D, or A B C naught D, or A B C D. Okay, so now we've included this term A B C D, which is one of the don't care conditions, so that will return a 1, but we didn't include the other don't care condition, A naught B naught C naught D naught, so now we've hidden the information 0, 1. Incidentally, this function, this function simplifies to A naught B C naught, or BD. Similarly, we could hide the information 1, 0 by removing the A, B, C, D term and replacing it with A naught, B naught, C naught, D naught. Remove A, B, C, D. We include A naught, B naught, C naught, D naught, and if we did that, we would end up with a simplified expression A naught, C naught, D naught, or A naught, B, D, or B, C naught, D. So all of these expressions are functionally the same as one another. They're functionally equivalent to one another if we consider that A, B, C, D and A naught, B naught, C naught, A naught, B naught, C naught, D naught are both don't care conditions. If we treat the don't care conditions randomly, we could have gotten any of these solutions and they would all be valid in terms of what our original specification was. But when we specify the output of the don't care conditions based on data that we want to hide, then the solution becomes unique, and we can use this idea to establish proof of authorship of the function.